All right, going to be working here on the homework for 8.3, which is titled The Integral and Comparison Tests. So I am looking at page, well, this book is page 453, and I'm going to use the, I'm going to be starting with number 9. So let's see here. Get some good fresh markers here. Get these out of the way. Okay, so number 9. Number 9 says, use the comparison test. Use the comparison test to determine whether the series is convergent or divergent. So we have sum n equals 1 to infinity of n over 2n cubed plus 1. All right. Well, if I'm going to look at a different series to compare this to, what I first think about is how does this behave if n is very big? So if n is very big, the denominator really acts like, so this is what I'm thinking over here. This is something like this series. If n is really big, then this really just acts like n cubed. The plus 1 and the times 2 doesn't really make a difference. And then on the top, it just acts like n. So it looks like maybe it's behaving like 1 over n squared because n over n cubed is n squared. So perhaps this is what I should compare it to. And I know what this series does because if we look at our sheet, this is a p series where the p here is 2, which is greater than 1. And if the p is greater than 1, then it will converge. So this is convergent. This is a convergent series. This is what I want to compare that one to. And the comparison test says that if this series is always bigger than this series, or each one of these terms is always bigger than each one of these, then the sum of all of those pieces should be bigger than the sum of these pieces. So here's what I want to show. I want to show that, let me get my notation right here. They call this one the a sub n. I want to show that a sub n is less than or equal to b sub n eventually. All right? If I can show that, my conclusion will be, so I want to show that. If so, then the sum of the a sub n's will be less than or equal to the sum of the b sub n's. And we already know that this goes to some number. So that means that our series has to be less than or equal to some number, which means that our series converges also. So let me try and show this inequality is true. Now a sub n for me is this. Remember the one I'm comparing it to is this. So this is my b sub n. So I want to compare those two sequences and show that inequality is true. So let me go ahead and write that down. I want to show this. So I want to show that n over 2n cubed plus 1 is less than or equal to 1 over n squared. So what I'll do is what we did before when we were dealing with like monotonic sequences and things like that, and that's just use algebra to try and come up with some nice concrete conclusion that this is always true. So what I'll do is I'll multiply both sides by n squared. When I do that, it goes away over here, turns that into an n cubed. And I'll multiply both sides by 2n cubed plus 1 here, 2n cubed plus 1 here, and so that'll just give me 2n cubed plus 1. And so when I compare these, let's see, if I subtract, let me subtract n cubed, subtract n cubed. I get 0 over here is less than or equal to 2n cubed minus n cubed is n cubed, and then plus 1. And I believe this is always true because remember, n is going to start at 1. So if n is 1, this is 2. If n is 2, this is 9. And obviously that's always bigger than 0. So my conclusion is that this is true, right? Therefore, since the sequence converges by comparison test, so does I'm getting kind of lazy with my n equal 1 to infinity here. So does this. Done. Okay? So notice I'm writing everything down. It's nice and logical. I had this. I thought about what I was going to compare it to. I identified what my a sub n and b sub n were, and went ahead and showed the inequality was true. Also, another thing I should point out is that in the comparison test, we have to have that a sub n is greater than 0, and we also have to have that b sub n was greater than 0. But that's true because this is always a positive number, because it's a positive number over a positive number. And then the other one I compared it to, this one, b sub n, that's always a positive number also. So that was true in my assumption. Probably should have stated that, but I'm stating it now. All right, let's do number 10. Same thing, sum, this time n equals 2 to infinity, of n cubed over n to the fourth minus 1 plus 1 plus 1 minus 1. Okay, so I think it says we want to use comparison test. So let me see, what would I compare this to? If n is really big, then that's acting like, the top is acting like n cubed, the bottom is really acting like n to the fourth. And so this is really looking like sum n equals 2 to infinity of 1 over n when I just reduce that out. So this is what I would want to compare it to. I do need to make sure that, well, I'll be a little more, be a little better with my notation here. I'm going to say a sub n is this one. And is that always greater than 0? Yes, because that's a positive number. And if n starts at 2, 2 to the fourth power minus 1, that number will always be positive. The ratio of two positive numbers is always positive. B sub n over here, 1 over n. And that's always positive. That's pretty obvious. So I'm going to be comparing those two sequences, but I need to know what this one does. Like if I'm going to compare it to something, I have to know what the thing I'm comparing it to does. So what does that do? Well, this is a harmonic series. We have 1 over a linear expression, or you could say this is a p series with p being 1, right? That's 1 right there. And so it's going to diverge. So this will diverges, all right? And if it diverges, then there's something a little different that I want to show. I want to show that a sub n is always bigger than or equal to b sub n. And my conclusion is that if so, then my series a sub n should be bigger than or equal to the series with b sub n. And if I know that that blows up and gets infinite, okay, or diverges, this one has to be bigger than that. That's also going to blow up. So I'm trying to force this one to blow up like this one does. Now let's see what happens. Remember, this is the inequality I need to show right here. If I can do that, then I know that since this diverges, that will. So let me go ahead and write down that inequality. I'll do it right here. I'm trying this. So I want to show a sub n is greater than or equal to b sub n. So I want to show that n cubed over n to the fourth minus 1 is greater than or equal to 1 over n. Do the same thing, multiplication, n to the fourth greater than or equal to n to the fourth minus 1. And if you subtract n to the fourth on both sides, you get 0 is greater than or equal to 1. Check, that's always true. Therefore, this inequality is true, and I can draw my conclusion. So here I come drawing my conclusion. Therefore, since the series n equals 2 to infinity diverges, sorry, equals to a 1 over n diverges, so does, or I'll say, since that converges, the comparison test can't write, says this series also converges, diverges. So notice that what I'm going to be looking for in your work, especially on a test, is that you are stating out your conclusion. You're working through all the inequalities correctly, and you're drawing your conclusion and stating the test that you used here. And so it's very logical, easy for me to look at and grade. If you don't state what test you're using and you just have a bunch of inequalities, you'll have points taken off. All right, let's do 11. Determine if it's convergent or divergent. So here we go. Sum, this is 11. N equals 1 to infinity. N to the 0.85, okay, 2 over n to the 0.85. Well, this is the same as 2 sum n equals 1 to infinity of 1 over n to the 0.85. And this right here is a p-series with p being equal to 0.85, which is less than 1. And because of that, if you look on your sheet for p-series, this would work with equal to, but if our p is less than or equal to 1, it diverges. So it diverges. And of course, 2 times the divergent series is still divergent, so this diverges by p-series. You could call it a test, I guess. That was pretty straightforward. Nothing to show there. You just have to identify what p is. Okay, 12. Sum n equals 1 to infinity of n to the negative 1.4 plus 3n to the negative 1.2 all right, well, I have the sum here of 2 terms, right? So I should be able to split this into 2 sums. But there's a little bit of an issue we run into here. Also, this is the same as 1 over n to the 1.4, then plus sum n equals 1 to infinity. And the 3, I'll put the 3 out here. And then 1 over n to the 1.2. So we are allowed to split this into 2 series as long as, and this is very important, as long as each one of these converges, then me splitting it up was okay. If it turns out that one of these diverges, then I couldn't split it up to start. So let's see what happens here. If I take this one, this is a p-series. P is 1.4, which is greater than 1, so it converges. Good. That's good to have because I know that I could split this one off. This one is also a p-series with p being equal to 1.2, which is greater than 1. Now, so that also converges. So if you add a convergent series to another convergent series, it's going to converge. So this one is a convergent, this one converges since it's the sum of two convergent p-series. There. So again, notice I'm stating my conclusion clearly. I'm stating why I'm drawing that conclusion. I have two convergent p-series, and the sum of two convergent series is convergent. So that's it. Let's look at 13. Notice I haven't used a comparison test yet. Let's see if 13 I need to. 13, all right, here we go. Now we're gonna have some fun. One plus 1/8 plus 1/27 plus 1/64 plus 1/125. Excuse me. I think I see this. Those are all perfect cubes. 2 cubed, 3 cubed, 4 cubed, 5 cubed, 1/1 cubed. Okay, so 1/1 cubed, 1/2 cubed, 1/3 cubed, 1/4 cubed, 1/5 cubed. So this is really just sum, n starts at 1 to infinity of 1/n cubed. And I hope this is obvious. This is a p-series. P is 3, bigger than 1, converges. That wasn't too bad. It's just really on that one, it's just finding the formula correctly. 14. 1 plus 1/2√2 plus 1/, I'm going to guess 3√3 plus, I'm going to guess 4√4, yeah, 5√5. Did I do plus ... on the last one? I don't know if I did. If I didn't, sorry. All right, well, that first one here looks to me like 1/1√1, 1/2√2, 1/3√3. So it looks like I just keep on going up, 1, 2, 3, 4, 5, and it's just the number and then times the root. So sum n equals 1 to infinity, 1/n root n. Yeah. So now let's just do some algebra. This is just sum n equals 1 to infinity of 1/n times n to the 1/2. That's what the square root means. And that's just sum n equals 1 to infinity of 1/n to the 3/2 when you add the exponents, right? 1 plus 1/2 is 3/2. And again now, this is a p-series. This is p being 3/2, which is greater than 1. Therefore, it converges. All right. So far, there's not really been much trouble here. Only really done the comparison test twice. See, 1/5 plus 1/8 plus 1/11, 1/14. Notice the denominator keeps going up by 3 each time, but it starts at 5. So how can I create that? How can I create the sequence 5, 8, 11, 14, 17. How can I create that? Well, I know that I'm going to have a 3n there because each time I go up by 3, but I want my first one to be a 5. So if I plug 1 in here, I need 5, I need to do 2. So let's see, if I plug in 1, I get 5. If I plug in 2, 6 plus 2 is 8. If I plug in 3, that's 9, plus 2 is 11. So really what I did is I took 1, 3, 5. No, you know what? I won't do it that way. I think I made enough sense. I don't want to confuse you. All right, so that should be it. I should have this equals sum, n equals 1 to infinity, and then 1 over 3m plus 2. Now, on a test, I would just say, hey, look, at this point, you could say it diverges because it's a harmonic series, because this is linear and this is a constant. But because this is the section on comparison test, I'm going to do a comparison. So let me try and compare that. I'm going to compare, I'll do the comparison one in red. I'm going to compare that to what? Well, the top, as n gets big, top just stays at 1. The bottom really just acts like n. And I know that this is harmonic. Or you could say P series with P being 1, which of course diverges. They're the same thing. All right, so I know this is a divergent series. So the comparison I need to do with this and this is I need to show that these guys are always bigger than these guys. So I need to show that 1 over n, 3n plus 2 is bigger than or equal to 1 over n. Also, I need to write down here, I'm looking at a sub n being 1 over 3n plus 2. I'm looking at b sub n being 1 over n. Both of these are greater than 0. Obviously, if n is positive, these are both going to be positive numbers. So I've checked that. I can use the comparison test. Let's go ahead and do our work here. When I do my cross multiplication thing, I get this, and then something bad happens. Watch. If I subtract n, I get 0 greater than or equal to 2n plus 2, and that is not true. If n is 1, this isn't true. If n is 2, it's not true. These are never going to be below 0 or equal to 0. So I've hit a catastrophe here. This is not working. I mean, we know this diverges. We know it does. But this comparison that I used, for some reason, did not seem to work out here. So let's think about how we might be able to tweak this so that it would work. What was the problem that I had when I did this? When I subtracted n on both sides, I got what do you get? 0 over here, and I still had n's over here, and that's going to get bigger. So wouldn't it have been better if I had n's on this side, and that way these n's got bigger and this side didn't get bigger? So how could I make more n's be over here? Instead of just n, I need maybe like 4n. And that way if I had 4n here, I subtract 3n, this n would get bigger than that side. So to get 4n here, I would have needed that down there to be a 4n. So let's go back here and tweak the problem. Hopefully you see that. If this is 4n, then when I cross multiply, that's 4n. We do our subtraction, it would go the other way. 3n out here, 3n out here, we get an n here, and then bigger than on this side, the only thing that would be there would be 2. And n is bigger than 2 eventually. Okay, so I'm tweaking things here to make things work for me. I'm going to come back to this. I'm going to change this. We said a 4n would work here. 4n. Now, is this still a harmonic series? Well, yeah, because that 4 you could really pull out as a 1/4, like that. And then you could say, well, that's harmonic, that diverges. 1/4 times that doesn't matter. It's still the same, diverges. So I'm going to compare it to that. I'm still going to say it's a P series with P being 1, it diverges. But now, over here, I change this to B sub n is 1 over 4n. And then my inequality is going to change. I still want to show this is true. So this is now 4n here. So now I multiply, I get 4n bigger than or equal to 3n plus 2. And then when I subtract 3n on both sides, I get n is greater than or equal to 2. Now, we all agree that this is not true right away. When n is 1, this isn't true. But what the important thing about the comparison test is that we need this inequality to be true eventually, like at some point, and then after that point, it's always true. So this would only work, right? This inequality would only work when n was bigger than 2, right? If n is 2, it's true. If n is 3, it's true. If n is 4, it's true. So eventually, this is true, which means that our series is always bigger than or equal to this series, and if this series goes to infinity, so does that one. So I'm going to draw my conclusion. Therefore, since sum n equals 1 to infinity of 1 over 4n, which is equal to 1/4 sum n equals 1 to infinity 1 over n, since this thing diverges, so does our series by comparison test. I'm using kind of different language in each problem, the way I'm writing my answer, just so you can see there's some flexibility here, as long as you get your point across. Since the original, since the series I was comparing it to was divergent, and this inequality held, my series is divergent also. Remember though, I said on a test, all you have to do is show that first part. Well, is show the, if this problem were on the test, you would just say, hey, that's harmonic, we're done. But I'm showing you how the comparison test would work for that. All right, next one. Number, where are we? That was 16? No, what was that? Did I miss 15? Uh-oh. I forgot to do 15. Darn it. Well, that's okay. I think I might not do 15 because I think 15 is almost exactly the same as the other one, 16. Hey, those are all odd numbers on the bottom, starting with 1 down here. So this is sum, whoa. Sum n equals 1 to infinity of 1 over, how do we create the odds? Starting at 1, 2n minus 1. And, okay, I guess I'll work it through. Shoot, I'm here, right, as well? All right, so if I looked at this, check it, it does work. This looks harmonic, okay, so it's going to diverge, and that's what you would say on a test. But if you're going to compare it, what we're going to compare it to is what we get when n gets real big. When n gets real big, this really looks like 1 over n. And that's harmonic. So I'm just going to run through this one real quick. This is harmonic. It's P series with P being 1. We know it diverges. We want to show that this, which is my A sub n, is always bigger than this, which is my B sub n. So I want to show that 1 over 2n minus 1 is bigger than or equal to 1 over n. And if we do this thing again, you're going to see it's not going to work. N greater than or equal to 2n minus 1. And when we subtract n on both sides, we get 0 bigger than or equal to n minus 1, and that's not true. So we run into the exact same problem we ran into on 16, and that's we need to tweak this. So hold on just a second. Okay, so now, if I want to tweak this, remember, I want to make this end bigger than this one so that this side's bigger than this. So I think the safest bet would try and make that a 3, which means make this a 3, which means make this a 3. But then that's still the same as this. which is still divergent. So look at my solution for number 16 I did before this. It's pretty much the same thing. We tweak it, and so you'll get the same conclusion, that this diverges. Okay. I also could have used like 5n here, 10n, it wouldn't matter. As long as I make that left side bigger than the right side, I would have been in business. All right, next one, number 17. I really do hope that you're trying these on your own before you're going to these videos. Watching me do it's a lot easier than you doing it. Okay, n times e to the negative n. Let me first write this as a fraction. So when I look at this, if n gets really big, you know, the top looks like n and the bottom looks like e to the n. There's not a whole lot more I can say about that. You might think, okay, well, n is linear and this is just huge exponential functions. So maybe I could compare this to something like sum n equals 1 to infinity of 1 over e to the n. You could maybe compare it to that. But then you'd have to figure out what type, you know, what does this one do? And if you look at this, this is actually 1 over e to the n, like that. And this is a geometric series with the base 1 over e, with r being 1 over e, which is less than 1. And so I know that this converges. I don't need to go figure out what it converges to, but I know that this converges. So let's try this. Let's try comparing this to this. And I don't know if this is going to work. So what do we need to show? What do I want to show if I want to show that my series also converges? I have to show that my series is smaller than that one, right? If this is bigger than that, then it could be infinity. So I have to make sure that this one right here is bounded by that series. So that means I need to make sure that this right here, a sub n, is always less than or equal to b sub n this time. So I want all of these to be less than all of these, or that's the same as this. This is my b sub n. Also, these are both greater than 0. Just look at them, let n be 1, 2, 3, 4. That's going to always be positive. So let's show this. And like I said before, I don't know if I'm going to be able to do this. So this less than or equal to 1 over e sub n. And when we do that, what happens? You get multiply across this side, you get n, e to the n, less than or equal to e to the n. Sorry, I don't know why I did that. I multiply both sides by e to the n, so this is 1 on this side. And that is not happening. So look, I don't know where my brain just went. Sorry about that, it's back. I multiply both sides by e to the n. I get n is less than or equal to 1. That is not true. And only, I mean, when n is 1, yeah, it's true, but when n is 2, 3, 4, it doesn't work. So this comparison doesn't appear to be working for me. What else could I do? Really, I don't see a way of making this side smaller than this side, like we did in the previous problems, like where we just came in with that 3 to make the ends work better. I can't seem to do that on this side, because if I make this like 4n, it's still not going to be true. What does that mean? It means that my comparison series didn't work. I need something else. I cannot say, just because this one converged and this inequality I couldn't get to work the way I want, I can't say, oh, okay, then it diverges. Can't say that. It's just that my comparison series sucked. Okay? It wasn't good enough. It didn't let me draw any conclusion. So the test failed, and I need to try something else to compare this to. So I have to start over, basically, is what I'm saying. Okay, so since that didn't work, I don't really see another series that I want to compare it to. So let me kind of go back to the beginning and think about what else is this section about. This section is also about the integral test. The integral test says that if we look at this series, right, and if we convert this sequence into a function of x, then if f is continuous on where's n starting? 1 to infinity. And f is positive on 1 infinity. And f is decreasing eventually so if we've got a function, if we turn this sequence into a function of x, so on the real numbers instead of just the 1, 2, 3, 4, 5, the integers, then as long as that's a continuous function, and as long as it's positive, so every time we plug in an x we get a positive number, and as long as it's decreasing, it's going down, then if the integral from 1 to infinity of f of x dx converges, so does that. If this integral diverges, so does that. So we have a lot to look at here. Can we even integrate this? Because we'll need to. Can we integrate this? So you look at that and you go, oh, well, wait, hold on. We did this like integration by parts. I think we can integrate that because we can use our ultraviolet minus voodoo to kill off the x, and then we'll have something nice in the other integral. So we should be able to integrate that. Is it a continuous function? Well, let me rewrite this. X over e to the x. X is a continuous function. E to the x is a continuous function. The quotient of two continuous functions is continuous as long as we never have division by 0. This is never going to be 0. E to the x is never 0. So you're never going to get division by 0. So it is continuous. Is it positive? I need to check. Is it decreasing? I need to check. So there's a lot of work to do in this. So here we go. I'm going to do it formally now. This is just me thinking. Okay. Let f of x be equal to x e to the negative x. Is f continuous on 1 infinity? Yes. It's the quotient of two continuous functions. Okay, first part's done. Is f positive on the interval 1 to infinity? Well, let me check. What does that mean? Is x e to the negative x greater than 0? Is it greater than 0? Well, again, we can look at it this way. Is that true? Well, as long as my x's come from 1 to infinity, as long as these are positive numbers, that numerator will be positive over that e to the any number is positive, and that is greater than 0, so that checks. So I've got the second thing. These are conditions I need to verify before I can use the integral test. Now, is it decreasing? Is it decreasing? Is f decreasing on 1 infinity. I forgot my question mark here. Well, to show it's decreasing, I'm going to want to show that the derivative of f is less than 0. Actually, this decreasing, it doesn't necessarily have to be decreasing the whole time. It's just eventually has to. Let's see. Okay, eventually. So it's like if I draw a function, it may go up. Eventually, it needs to come down and keep going down forever. So maybe over here it's increasing, but eventually after some point right there, it's decreasing from there on out. That's what we need. And this doesn't have to be 1. 1 can be back here. This could be 5, and eventually it goes down. So let's see. Well, I need my derivative. So what's the derivative of x e to the negative x? Well, I can use the product rule. Derivative of x is 1 times e to the negative x, plus derivative of e to the negative x, which is e to the negative x, times negative 1, because that's derivative of what's up here, times the x from the front. So we're getting, let's see, I can factor in e to the negative x out of both. 1 minus x. So my question is this less than 0? So let's check it out. I'm at a room here. So is that less than 0? Well, this right here, I'm going to rewrite as 1 minus x over e to the x, dropping this down. Is that less than 0? Question. Well, what do we know about the numerator? If x is 1, this is 0. If x is bigger than 1, then this is going to be bigger than 1. So 1 minus this number should be a negative number. So I should get a negative number on top. E to any number is positive. Negative divided by positive is always less than 0. This is true if x is greater than 1. But that's good because that's what we wanted. See, at 1, I don't care that it is 0. I don't care that it's 0 at 1. Bigger than 1, so eventually this inequality does true and it holds the rest of the way. So yes, the answer is yes, we have a decreasing function. So we've got everything we need in order to use the integral test. Now we get to use it. So let's figure out what the integral of this thing does. What is the integral from 1 to infinity of x e to the negative x dx? So I'm going to use integration by parts. I'm going to first just look at the indefinite integral over here. U dv, let u be x, dv be e to the negative x dx. Differentiate down, integrate up. Careful with that negative, you have to account for it out there. So this is going to be ultraviolet minus integral of voodoo, which is this times this. And notice that negative there? Times this, I'm going to bring that negative and make it a positive, e negative x dx. And then this turns into negative x e to the negative x. Antiderivative of that is negative e to the negative x. So that's my antiderivative. So over here, I get, now notice we have an infinite limit. So I've got limit as t goes to infinity of integral 1 to t of x e to the negative x dx, which equals now the antiderivative, so limit t goes to infinity of negative x e to the negative x minus e to the negative x evaluated from 1 to t. And I don't really care for this version of it. I'm going to do something a little different. I'm going to do limit t, well, you know what? T goes to infinity. I'll go ahead and do it right now. All right. So if we plug in t, we get negative t, e to the negative t, minus e to the negative t. Okay, if we plug in 1, we get, so minus, if we plug in 1, we get negative 1, so negative e. Negative negative 1 is 1, so 1. And then minus, again, 1 in here. Wait, did I say negative negative 1? Oops. I'm plugging in 1. 1 goes in there. 1 goes in there, okay. Minus e to the 1 again. Close that off, and then the limit. All right. Gosh, man, I'm making all sorts of mistakes on that. You know what? I said I was going to switch it. This is right, but let me switch it because I really don't like the way that looks. I just don't like it. So I'm not going to actually do the t and the 1. What I'm going to do is rewrite this first. And watch how I'm going to rewrite it. I'm going to pull out an e to the negative x. Let's make it a negative e to the negative x. I'm left with x plus 1 if I do that. And then I'm going to take this and drop it below as a positive x. And then, you know what, I had that negative. Maybe I'll just leave it out there, negative like that. So this is going to be limit, t goes to infinity, negative x plus 1 over e to the x evaluated 1 to t. I like that a little better. So now, limit t goes to infinity of, let's see, t goes in first. I get t plus 1, so negative t plus 1 over e to the t minus, now I plug in 1. I get 1 plus 1 is 2, so negative 2 over e to the first power, so that's that. Now let's let t go to infinity. If I let t go to infinity, this becomes infinite. E to the infinity also goes to infinity. I get infinity over infinity. So I can actually use L'Hopital's rule here. L'Hopital's rule says that I just need to take derivative of the top and bottom separately. The derivative of the top here, right here, is just 1, and then there's a negative. And derivative e to the t is itself. Minus, now I'm not touching this one. So I really just did L'Hopital on this. And now as t goes to infinity, this goes to fixed number over infinity, that goes to 0. And so my answer is going to be this together is plus 2 over e. So this integral goes to 2 over e, which is a number. It converges. And since this converges, my series converges. Now, I'm not saying that my series goes to this. I'm just saying that my series converges. So, therefore, since the integral 1 to infinity of x e to the negative x dx converges, so does the sum n equals 1 to infinity of n e to the negative n by the integral test. Done. It's a lot of work. It's a lot of work for that problem. All right, how's my time here? 48 minutes. Let me see if I have time for another one. Yeah, let's do 18. Okay. Sum n equals 1 to infinity n squared over n cubed plus 1. All right, so if I were doing this problem, initially, I would look at it, I'd say, okay, I want to compare that to something. I would like to compare that to this. N squared over n cubed, because that's what it's really behaving like, which is 1 over n. This is a divergent harmonic series, so I would do my comparison. I would need to show that that is bigger than this. The n squared over n cubed plus 1 is bigger than this. So real roughly, let me just lay out how this would be working, although I'm going to do it a different way. I would need to show this. And if you did it, n cubed greater than or equal to n cubed plus 1. And then this, when you canceled, you would get 0 is greater than or equal to 1, and that's never true. And so you could tweak it. You could try and make this side bigger than 1, and you could do it. You'd probably have to come in here, maybe like with a 5. That would make this a 5. And then when you do your subtraction, it would work. And so it could be done that way, and I'm not saying not to do it that way. But I wanted to show you that you could also do this using the integral test. So let's see. Integral test, the reason why I'm thinking integral test is because I know that if I convert this over to a function, if I let f of x be equal to x squared over x cubed plus 1, I can integrate this pretty easily because I can let u be the bottom, the derivative of that is up there almost. So I have basically a basic substitution on this, which is nice. The problem is that I have to show f is continuous. Is that true? Well, continuous function over continuous function. Yes, the only time the bottom can be 0 is if x is negative 1, but that's not where we're looking. So this is continuous function on the interval 1 to infinity, that's fine. Is f positive? Well, that's a positive number over a positive number as long as x is bigger than or equal to 1. So yes, on 1 infinity it is. And then the next thing is f decreasing? So in order to show that, eventually, right, I need to look at the derivative of this. And I just use a quick quotient rule on that. 2x, x cubed plus 1 minus 3x squared times x squared. There's my quotient rule all over the bottom squared. So this is 2x to the 4th plus 2x minus 3x to the 4th over x cubed plus 1 squared. And when I put those together, let's see what I get here. 2x minus x to the 4th over x cubed plus 1 squared. I can factor an x out of the top, x 2 minus x cubed over x cubed plus 1 squared. So there's my derivative. The question is whether or not that's negative. So is f prime less than 0 eventually? So is that less than 0? Let's see. X times 2 minus x cubed over x cubed plus 1 squared. Is that less than 0? Well, I know the bottom is always positive, right? Because I'm squaring it right there. So I know the bottom is positive. It really doesn't play much of a factor here. I know that if I'm plugging in things like from 1 to infinity, I know that this right here is positive. The only question then is this piece right here, 2 minus x cubed. I need this to be negative, because then I'll have a negative times a positive. That'll be negative over a positive, that's negative. So the question is this negative? Well, if x is 1, no, right? That's going to be just 1. If x is 2, though, I get 2 cubed, that's 8. 2 minus 8, that's negative. So from 2 on, it's going to work. So is f decreasing? Yes, eventually it is. It's eventually decreasing. I won't say where, but it just eventually is. It's after 1 somewhere. So I have everything I need to use the integral test. So I need to find the integral. So I look at the integral from 1 to infinity of x squared over x cubed plus 1 dx. Convert this over just to an indefinite integral real quick so I can find the antiderivative. Make a basic substitution of the bottom. There's du. 1/3 du equals x squared dx. So I'm going to replace x squared dx by 1/3 du. I'm going to replace x cubed plus 1 with u. So this integral becomes 1/3 1 over u du. And then that becomes 1/3 natural log absolute value u. Plus c, but we're going to come back up here now. So this becomes, I better do it over here. that becomes limit t goes to infinity, because I have that thing up here. The antiderivative of this is this, 1/3 natural log, but what was u? U was x cubed plus 1. Evaluate it from 1 to t. And now, when we plug in limit t goes to infinity, let's plug in t first. 1/3 natural log absolute value of t cubed plus 1. And then minus 1/3 natural log. When we plug in 1 here, we get 1 cubed plus 1, that's 2. So natural log of 2. And now let's let t go to infinity. If t goes to infinity, this is infinite. Natural log of infinity goes to infinity times 1/3. So this whole thing goes to infinity minus whatever this number is. And that's going to go to infinity. And that means it diverges. That's a g. So therefore, since the integral from 1 to infinity of x squared over x cubed plus 1 dx diverges, so does the integral from, not the integral, the sum that we're looking at, this sum, the series, sum n equals 1 to infinity of n squared over n cubed plus 1. Why? By the integral test. So I think you can say pretty easily on this example that it would be preferable to do this problem the first way I showed you, by using the comparison test. But I'm just showing you that for this particular problem, and a few of the ones we did before, we could have used the integral test to do it. Where am I at? 10, 15, 7. I think that's good. I'm going to put a little mark on my page here. I finished up on 18, so I'm going to start. Okay, ended on 18. I will start with 19 on the next video when I have some time for that.